In today's video, we are going to discuss about volumetric, the analysis of citric acid concentration in lemon juice using sodium hydroxide. Let's get to it, but first we are going to introduce our group members. Let's dive into the introduction of volumetric analysis.
Titration, often known as volumetric analysis, is a process of grading a substance having a known volume and concentration with another chemical with an unknown concentration, also labeled as the general name for a quantitative chemical analysis method which determines the volume that the substance occupies in order to determine its amount. Moreover, it works by measuring the volume of the liquid needed to react completely with another solution of known concentration. This method is especially useful when high accuracy is needed in chemical measurements. One of the most widely used types of volumetric analysis is acid-base titration. This involves slowly adding an acid to a base or a base to an acid until they neutralize each other. The equivalent point is a point at which the reaction is finished. Thus, a chemical indicator was used to help determine this point of interest. When the acid and base are balanced, the indicator changes color to indicate that the titration is complete. Furthermore, in laboratories, acid-base titrations are commonly used to test the strength or concentration of acids and bases because they are easy to use, fast, and result in accurate findings. Most of the industries such as environmental testing, medicine, food safety content, and education extension in using this grading method.
Now we're going to look into the theory of this experiment. Let's go. Alright, so what is the relationship between determining the concentration and titration? We are going to look a little deeper as to what titration method is being used in this experiment. Let's begin with citric acid. Citric acid is a weak tripartite organic acid with a chemical formula of C6H8NO7. It contains 3 carboxylic acid groups presented by CEOH. Physically, it appears as a white and odorless crystalline solid and is known for its decently sour taste and naturally present in citrus fruits like lemon and oranges. In water, citric acid only partially ionizes, which makes it a weak acid. So the question is, where do we get citric acid naturally? We can get them in fruits like lime, orange, strawberry, grapefruit, pineapple, and raspberry. But which fruit contain the highest amount of citric acid? Of course, the king of the king is lemons. Now let's talk about sodium hydroxide. Sodium hydroxide or NaOH is a strong ionic base. It fully dissociates in water to produce sodium ions Na+ and hydroxide ion OH-. This complete dissociation makes it a highly reactive and strongly alkaline substance. When citric acid reacts with sodium hydroxide, a neutralization reaction occurs. The product of the reaction are sodium citrate and water. In this process, the acidic hydrogen ions from citric acid are replaced by sodium ions from NaOH, forming salt sodium citrate. This is a classic example of an acid-base reaction between a weak organic acid and a strong base. Now that we understand the chemical background, let's move on to the methodology used in our experiment.
Materials for this experiment is sodium hydroxide, diluted lemon juice, phenolphthalein indicator, burette, red torch stand, burette clamp, pipette, ball pipette, beaker, conical flask, white tile, and funnel.
Now let's move on to methodology. First is the lemon juice preparation. We need to filter lemon juice to remove pulp. A known volume of lemon juice is diluted with distilled water to make it suitable for titration. Next step is set up the burette, retort stand, and clamp as shown in the diagram. Next, we need to rinse the burette by adding 10 ml of sodium hydroxide to the dry burette and let the solution run through burette tip to a base tip. Complete this process a total of 3 times. Then, fill the burette using a funnel so that the meniscus of the NaOH solution is above the 0 ml. Let some of the solution run rapidly from the burette to expel all the air bubbles from the tip and bring to below the 0 ml bottom. By using a pipette, transfer 20 ml of the diluted lemon juice into a clean conical flask. Add 6 drops of phenolphthalein indicator. Then, place a conical flask under the tip of the burette and place a white towel under the flask to make it easier to see the color changes. While continuously swirling the flask to ensure thorough mixing, run the sodium hydroxide solution from the burette. Initially, a red or pink color will appear at the point where sodium hydroxide comes in contact with the solution in the flask.
As the endpoint nears, the color will disappear more slowly. Eventually, the sodium hydroxide should be added drop by drop until the red or pink color caused by 1 drop of sodium hydroxide remains for at least roughly 15 seconds. The trick to this titration with a pre-colored reaction mixture is to have some but not too much stirring or swirling of the reaction mixture.
Lastly, read the final volume of the liquid and write the volume of NaOH solution used in your data table. Remember that the scale increases as you go down.
Lastly, refill the burette and complete the titration twice more. Next, we have example of results.
In this part, we will determine the concentration of nitric acid solution using titration. A student used 25 ml of 0.050 molar sodium carbonate and the average volume of nitric acid required is 22.38 ml. Step 1 is to write the balanced chemical equation. It shows that 2 moles of nitric acid react with 1 mole of sodium carbonate to form sodium nitrate, water and carbon dioxide. Next, we calculate the moles of sodium carbonate using the formulas moles equals concentration times weight volume. So 0.050 times weight 0.025 give 0.00125 moles. For step 3, we apply the 2 to 1 mole ratio. Multiplying 0.00125 by 2 give us 0.00250 moles of nitric acid. Finally, we calculate the concentration using the formula C equals N over V. Dividing 0.0250 by 0.02238 gives a concentration of 0.11 molar. So the experiment shows that the nitric acid solution has a concentration of 0.11 mole per liter.
Here, we are going to talk about some of the experiment errors.
Now, I'm going to talk about some of common experiment errors in titration, their types, and examples so we can learn how to avoid them in the future experiments. Firstly, most of the time, we will misread using the burette, which is a human error. This happens when the burette reading is taken from wrong angle that is not at eye level. Looking from above or below the meniscus level can lead to incorrect readings. For example, a student records the volume as 25.6 ml instead of the correct volume, which is 25.4 ml, just because they look from an angle. Next, we have a random error that happens when failing to recognize the endpoint properly. Sometimes students might miss the exact moment when the indicator changes color. This can cause them to either stop early or add too much titrant. For instance, a student adds too much titrant after seeing the color starts to change and end up overshooting the endpoint, which makes the results too high. Lastly, systematic error can occur where we use dirty equipment or wet apparatus before starting the experiment. If the burette or pipette is not clean or still has water inside, it can dilute the solution, leading to inaccurate results. To illustrate, a student raises the pipette with distilled water instead of the sodium hydroxide solution. Then, a small amount of water remains inside the pipette and dilutes the sodium hydroxide, leading to inaccurate concentration and unreliable results.
Then, we have future recommendations for this experiment.
Now, allow me to share some recommendations for improving the accuracy and reliability of this titration experiment in the future. First and foremost, using a burette with finer markings can really help improve accuracy. Finer divisions like 0.05 ml instead of the usual 0.1 ml will allow us to take more precise reading of the liquid volume. This reduces the need to estimate between lines, minimizes human error, and makes it easier to control how much solution is added, especially near the endpoint. With more detailed measurements, we can get results that are not only accurate but also reliable. In addition, doing more trial is another important step. By repeating the experiment several times, we can reduce the effect of random errors. More trial makes it easier to spot any odd or inconsistent results, and calculating an average gives a clearer picture of the actual value. This also helps confirm that the method we use is consistent and the result weren't just due to chance. The more times we do the experiment, the more confident we can be in the outcome. Last but not least, we recommend swirling the flask consistently and using a clearer indicator. Swirling ensures the solution are mixed properly so the reaction happens evenly throughout the flask. If mixing is uneven, the titrant might not fully react, which affects the accuracy of the results. Also, a clear and sharp indicator makes it easier to see color change at the endpoint. This also helps avoid overshooting or missing the endpoint altogether, which can cause large errors in volume readings.
Last but not least, we have the conclusion for this experiment.
To end our topic for today, let me share the conclusion of our titration experiment. In conclusion, this experiment was aimed to determine the concentration of citric acid in lemon juice by titrating it with a standardized sodium hydroxide and NaOH solution. However, based on our results from the experiment, it shows that only small volume of nitric acid, which have an average of 2.238 ml, was needed to neutralize 25.0 ml, of 0.050 mole per liter sodium carbonate solution. This suggests the nitric acid solution being tested is relatively concentrated, since only small amount was sufficient to react completely with the standard base. The results were also very consistent, with the trial volumes ranging only between 2.235 to 2.240 milliliter, also indicates that the experiment was precise and consistent, with minimal variation between trials. This consistency increases confidence in reliability of the average volume used in further calculations. Therefore, the titration results were impressively consistent, giving us solid average volume that can be confidently used to calculate the concentration of the nitric acid solution. These are our references. That's all from us. Thank you for listening.